Welcome to Late Night Chemistry with Mr. Harden. Today's episode, photoelectron spectroscopy. Photoelectron spectroscopy is one of a couple of minor topics that we haven't talked about so far in AP Chemistry, which means that all the other minor topics and major topics we have talked about. Now, photoelectron spectroscopy is also known as photoemission spectroscopy. But if you want to play it safe, you can just call it PES because that works equally well for either one of them. Basic idea is actually pretty simple. In this illustration, we have a metal plate and we're striking it with a high energy photon. Now this photon, you'd know the wavelength and frequency, so you could calculate the energy. So high energy would be high frequency or really short wavelengths. Now when it strikes this metal plate, if it has sufficient energy, it will kick out an electron. The idea is that you measure the energy of the electron that is kicked out from this process. Now the difference in energy from the incoming photon and the outgoing electron, well, that difference is the binding energy of the electron. How much energy is holding the electron to the atom. Let's take a look at an actual, my drawing of an actual PES spectrum. Now, you can do PES for things like compounds, but probably in an AP Chemistry exam, they're just going to limit you to talking about elements. So this is the spectrum for lithium. Now to get this spectrum, they are collecting the data of the energy of the photons going out, so that's the wavelength or frequency of the photons, they're striking it. The energy of the electrons is being emitted. And the number of electrons. And when they put those together, they usually display it in a graph format like this. They plot it out. The x-axis is the binding energy. That's be the difference in the energy of the photon coming in and the electron going out. Units, millijoules per mole. If you look at the axis, there's something quite interesting. Actually, two things quite interesting. One, they're not starting at zero. Instead, they're starting at a rather large number and going down. And the second is that this is a logarithmic scale. So each one of those big squares, the 5 smaller squares, is a factor of 10. So you've got this spot over here that's like 1,000 megajoules a mole. That's 100. That's 10 times smaller, 10. So the reason they do this, if they try to put this all on one consistent scale, you would have a huge amount of space in between those individual peaks. This way we can kind of see it all together. Now on the y-axis is the number of electrons. It's kind of a relative number of electrons. But if you know how many electrons are totally involved, you can actually convert that into the number of electrons that have that particular energy. Now, lithium. You may notice that boron highlighted. Lithium nowhere in the sight. That's because, despite what I wrote down on that, that was actually the PES spectrum for boron. Now, boron has 5 electrons, so all those peaks would add up to 5, so they can figure out then how much each peak corresponds to in terms of number of electrons. Let's look at it again with one little correction. Okay, this is the PES spectrum for boron. Now, boron has 5 electrons. So all those peaks would add up to 5. So you end up with 2 peaks. They're both twice as tall as the last remaining peak. So this little guy is 1 electron. And these are 2 electrons. and there's another 2 electrons. So you've got 2 electrons that have considerably more bonding energy than the others. At 19.3 megajoules per mole, it's that more than 20 times the smallest number of smallest bonding energy, and is still considerably more than the other one. Now, does this remind you of anything? Let's think back about what you know about beryllium. How about its electron configuration? So, why don't we write it out real quickly? Well, electron configuration for boron is 1s2, 2s2, 2p1, which tells you there's 2 electrons in the 1s sublevel, 2 electrons in the 2s sublevel, and 1 electron in the 2p sublevel. And because the 1s is at a lower energy level, it would have a considerably more energy to remove electron from that energy level. That's the reason the 1s electrons have much higher binding energy than the electrons you'd find in the second energy level. So this one comes from the 2s2. There's 2 electrons in there. It's a little bit more energy than the 2p. The 2p is high in energy, so that means less binding energy you have to supply to remove it. So if you think of it in terms of electron configuration, there is a really nice match for the PES and the electron configuration that we talked about oh so long ago. The reason that we're using the reverse scale from high to low is that way it's going to match what we'd normally write down for these electron configurations. Okay, this is the PES for magnesium, and let's see if this matches what you might expect. Okay, the electron configuration for magnesium will be 1s2, 2s2, 2p6, 3s1. So very first peak at that really high value of 126 megajoules per mole is where you'd find your 1s electrons. Just under 10 megajoules per mole, you're going to find your 2s electrons. And then write down the exact number for the 2p6. And then much easier to remove, though, of course, is going to be the 3s electron because it's from the highest energy levels. And so why the electrons in A have greater than 10 times the bonding energy of electrons you'd find in B? Well, A is just from a inner energy level. The lower energy level, the higher the energy. So why is peak C 3 times the size of peak B? Well, because that's 6 electrons instead of 2 electrons. So it's just a direct match for your electron configuration. Think about the other way around, though. It's a confirmation of all these ideas that we've been talking about electron configuration. You can see experimental evidence to show that's the way the chemists have already said this works. It actually does work. Let's take a look at example 3. Okay, for example 3, we're going to use this topmost PES spectrum. I was just pausing the video right here. See if you can identify each peak, figure out which element we're talking about for element, well, for example 3. Okay, hopefully your pause is over, and let's see if you get the same sort of results that I would. Okay, identify the peaks as 1s2, 2s2, 2p6, 3s2, 3p3, which would make the element in question phosphorus. Now, example 4, let me do a little straightening. Okay, this is what I want you to do. Okay, I want you to sketch the PES spectrum for the element just before phosphorus. So again, a little pause, and let's see what you can come up with for the PES of silicon. Okay, I've drawn the first peak. Notice that the binding energy is slightly less for silicon than its phosphorus. So as the nuclear charge would increase, the amount of energy required to remove an electron would also increase. So it should still be a really high number because it's from that first energy level. And that's for an element with so many protons, the first energy level would require a ridiculous amount of energy to remove. But a little bit less than for phosphorus. So all the corresponding peaks you can see for silicon are going to be a little bit lower energy than they would be for phosphorus. So let's go ahead and start sketching in the other peaks. Okay. So you expect to have a 2s2 and 2p6. A little bit lower in energy than the phosphorus example. 2p6, going up to 6 electrons because it has 3 times many electrons in that sublevel as the 2s. The last two peaks will be 3s2 and 3p2. Both those would be the same height as they both only have 2 electrons in them. Okay, we do have one more example. Okay, last example. What element is this? Okay, that's a little bit better. So match each piece to its electron configuration. Again, I would pause, write down what you think it is, and then we'll talk about it afterwards. Here's a little bit of space for pausing. Okay, the element involved would be scandium. So let's wrap the electron configuration scandium, and then we'll match it to all these peaks. Okay, so we've got peaks for 1s2, 2s2, 2p6, 3s2, 3p6, and then this little half-size peak. Okay, so this is 2 electrons. That half-size peak would be 1 electrons. So that's the 3d1, and then the last peak's the 4s2. So is that a surprise? Well, when you're filling in electrons, you would put in, if you're following the periodic table, which are a nice guide, it would tell you to do 4s2, and then, say for calcium, it would be ended up with 4s2. And the next one you put in 3d1, and that would give you a correct configuration. But For scandium, 3D1 actually has less energy than the 4s electrons. Well, sorry, did I say less energy? You look at that chart, that's not less energy. It has more energy. It's got more binding energy than the 4s2. The energy to remove a 4s2 is going to be less than it is a 3D1. Now, when you think about it as in you start to remove electrons from scandium, the one you'd remove first would be the 4s electrons, because those 4s electrons have the smallest binding energy. It takes the least amount of energy to remove. You only remove the 3D electrons after both the 4s2 electrons have been removed. Now, the 3D one is lower in energy. Well, the 3D1 has more binding energy than the 4s2. Then how does that explain why in magnesium you would put in just 3p6, not magnesium, calcium? You do the 3p6, and then immediately the next thing you do is a 4s2. Why would you skip over the 3d1? Well, the 3Ds, it all depends off of a couple of factors. It's always the fun things when there's more than one factor. Because if there's just one factor involved, you have really straightforward patterns to everything. So, one important thing is energy levels. The higher the energy level, the further it is from the nucleus, the easier it is to remove. That's the reason the 4s are easier to remove than the 3Ds. But calcium, compared to scandium, also has a lower nuclear charge. So for magnesium, after the 3Ds, it puts in the 4s because it doesn't have enough pull to pull those electrons down to the 3D sublevel. 3D sublevel is closer to the nucleus than the 4s sublevel. It's more crowded is the reason why it ends up being higher in energy. By the time you reach scandium, though, it has enough pull to pull down that electron into the 3D1 sublevel. Once one is there, you've changed the electronic environment, and after that, because of now the extra repulsion, it'd be too hard to pull any more into the 3D until you had more nuclear charge, so instead they start showing up to the 4s. So even though you learned a way, and it's a good way, it doesn't give you the right answers, you're always really putting in the 3Ds before you put the 4s, even if you're used to writing as 4s2, 3D1, and you're filling it in that order. The actual order the electrons being filled in is a little bit different. So this was your adventures into PES. Once you realize that that's just a matched electron configuration, I think these sorts of problems should be easy enough for you. Thanks for tuning in.